Okay, so good morning, everyone, and thank you for joining us. Today, we have the real privilege of welcoming Professor David Bercovici from Yale University, who is going to tell us about the generation of plate tectonics from the grain scale up to the plate scale. So, David, I'll leave you the floor.
All right. Thank you very much, Catherine. Thank you very much, everybody, for the invitation to come talk to you about this research. So, as Catherine said, I'm going to start off, well, here, I mean, we always start off with a bit of an outline. Let's see if I can get this to work. Well, let me first of all acknowledge a large number of collaborators, former students, postdocs, experimentalists, theoreticians. I'm not going to name everybody here, but you can see various people that have been involved with the research over the past many years, 20 or more years. So just as an outline or a roadmap, give you an idea where we're going. First, I want to give you, of course, some background about plate tectonics and mantle convection. Discuss what we typically call like the plate generation questions and lithospheric deformation, and then dive into some of what we call grain scale physics or grain scale processes that we think are necessary for explaining why we have plate boundaries forming on Earth out of a convecting mantle. And then I'll show you some applications of this theory. I mean, it's a theory that I guess I generically have called grain damage theory. Some applications of this that have to do with whether or not we can predict whether we have plate tectonics on, well, of course we know we have it on Earth, but whether we can have it on Earth or other planets. And when did plate tectonics start? Sort of trying to address the question of when did it even begin on our planet? And that number is all over the place, and we'll get to that. And then I'm going to spend the last bit talk about the most recent research was trying to understand a bit about how grains and mineral phases mix at the grain scale and why that's important for developing plate boundaries, and also show some applications to that recently, in addition to some comparison to lab experiments, and then we'll finish up. Okay, so when we're all taught about Earth plate tectonics, of course, the first thing we're taught is how important it is for inferring the location of earthquakes and volcanoes, since most earthquakes and volcanoes occur on plate boundaries, and they also, the sense of plate motion tells us what kind of earthquake and what kind of volcano we're typically going to have. And of course, it's interesting because, of course, the bottom line of this is always that subduction zones generate the most violent volcanoes and the most violent earthquakes. But also what's very important is that the mode of volcanism, especially due to subduction, is very unique to the Earth. And the mode of development of continental crust associated with subduction is very unique to the Earth, as far as we know. Okay. So it's also very important to tell us, not only about the events, but about the types of events. But in addition to that, plate tectonics is important for explaining, why our planet seems to be unique. It's one of those particular ingredients for saying why there is liquid water, why there's life on our planet, why there's a temperate climate. And it's been hypothesized and tested for over 40 years now. The idea that plate tectonics, by constantly exposing minerals to the surface, has been responsible for scrubbing most of the CO2, carbon dioxide, out of our atmosphere. And it also provides a negative feedback by which if things get warmer, it scrubs out CO2 faster. If it gets colder, the CO2 builds back up again. And it's a regulator for the climate over tens and hundreds of millions of years, which is why it's thought to be an important ingredient for habitability on our planet, and perhaps an ingredient for habitability on other planets. So, for example, even recently, as of today, in fact, there have been 5,000 pushing towards 6,000 confirmed exoplanets. Not all of those are terrestrial planets, but about 200 are terrestrial, and about 1,600 are super Earths, terrestrial planets that are not quite 10, but maybe 3 or 4 masses of the Earth itself, but are still considered terrestrial planets. And one of the ways of trying to say something about the habitable zone, whether or not these are habitable or have liquid water, is not only their proximity, their closeness to their host star, but also whether those would lead to the conditions that we think we have on Earth with regard to plate tectonics, keeping the Earth's climate pretty habitable, or pretty something that doesn't wipe out life and turn us into Venus. Okay, all right. So let me kind of go to the beginning of simple stuff with regard to convection. You usually think of that the Earth formation is about 4.6 billion years ago. I mean, I say at the beginning, that skips about 9 billion years of universe's history, but we can start with the Earth anyway. And it's an important part. I mean, all types of research goes into solar system formation, planet formation, but as far as mantle convection is concerned, one of the important components of this is that the energy source that drives convection is probably still what's left over from the formation of the planet. When the planet accreted, the collision of bodies winds up being stored, converting all this kinetic energy to thermal energy, and it's stored still as primordial heat. And probably more than 50% of that is still coming out of the planet 4.5 billion years later to drive convection. So now the total amount of heat coming out of the planet is about 46 trillion watts. And probably more than half of that is from this primordial heat left over from the accretion of the planet. Probably less than half of that is from the decay of radioactive elements like uranium and thorium that are intrinsically in trace amounts within minerals and rocks. A lot of that gets partitioned to the crust because of how crust is formed during melting. So a lesser amount of it is still stored in the mantle. Nonetheless, even though 46 trillion watts sounds like a big number, it's not a very big number. If you were to compare it to how much energy is put out on the surface, it's much smaller, of course, than what we receive from solar energy. 4,000 times smaller than what we receive on a daily basis from the sun. It would be the equivalent of trying to light up an entire soccer stadium or football stadium with about 2 light bulbs. Okay, so it's a weak source. But that source of energy is focused into convecting currents, into where the mantle is fluid and it flows, and where it's cold near the surface, it sinks in these blue blobs on the left, and what we normally think of as subduction zones. So these big sheets of downwellings are the equivalent of subducting slabs. And of course, hot material near the core can rise and develop plumes. This computer simulation probably overdoes the amount of plumes. We typically see these things in like maybe Hawaii or Iceland. Of course, the mantle convects very slowly, but the important part is that weak energy source is focused into these currents that then drive circulation in the mantle, and then in the end are expressed as plate tectonics. I mean, sometimes we hear the term that mantle convection drives the plates around like conveyor belts or rafts, but really that's kind of a wrong perception that plate tectonics is convection, that subducting slabs are the downwellings, and that the plates are moving around as part of what's called the thermal boundary layer of the convecting mantle. But what's important about the Earth style of convection, as far as we know, it's one of the only forms that, of course, the convecting currents are visible as motion all the way to the surface, and it's in the form of plates, and they also bring material all the way to the surface that involves circulation of minerals to the surface and then drawing down volatiles like carbon dioxide and water into the mantle. So there's a complete communication between the mantle and the atmosphere and the ocean, which is important for, again, keeping the climate the way it is. Okay, so that's the big picture stuff about convection. The plate generation questions about why do we have plate tectonics? These are big questions, of course, but there are very specific ones that you can break them down. For example, something I've been chasing probably over 30 years is why do we have plate tectonics arise from a convecting mantle? If I get the mantle cooking and it's convecting, why does our planet look like plate tectonics, but not on Earth and Venus? And what is the basic physics that governs whether we can expect to find this on another planet? And then the other bigger questions are how and when did plate tectonics emerge? I mean, it may very well be that our early Earth, when it was probably had a very thick atmosphere, not unlike Venus, maybe it looked like Venus. I mean, sometimes it's been proposed that Venus is not a bad copy or model of what the Earth may have looked like, about 4 billion years ago or so, right after the magma ocean. Okay, so let's just keep going. So one of the, convection is one of these universal processes, right? Hot stuff rises, cold stuff falls. We see it in the ocean, we see it in the atmosphere, we see it in the sun. They all have their unique versions of what makes them difficult. It could be turbulence, it could be magnetic fields, it could be clouds, who knows, okay? But in the Earth's mantle, we don't really have turbulence. It's a very slow moving rock fluid. It's still a fluid, even though it's solid. And that's kind of the important part of this diagram. And because it's solid and moves in crystalline form, its rheology, in other words, how it deforms, is very complicated. And it depends on a lot of things other than just if I push on it, it moves. It depends on properties that are inside the crystal and the mineral itself. And so these are just an example. If I look at the stress, the differential stress pushing on something versus the temperature, it can deform in different ways depending upon how hot it is. So at very high stress and high temperature, it undergoes what's called dislocation creep. And there's a simple little diagram above with this dislocation glide of a jog, basically a missing crystal row in the crystal lattice, is shuffled along to accommodate deformation from the top to the bottom. Alternatively, you can also have, for example, at lower stresses, diffusion creep, where if I squeeze a grain, the atoms will diffuse away from where it's being squeezed to where it's being under tension, right? So it can diffuse through the middle of the grain, or it can diffuse on the grain boundaries. And the more grain boundaries there are, the faster it will diffuse, because they provide channels or easy pathways for atoms to diffuse. Either way, both of them obey. I'm going to try not to show too many equations in this talk, but there's going to be a few. Either way, it obeys this rheological law, in which this E dot is strain rate, how fast things deform, and they're functions of this sigma, this Greek letter sigma, which is stress. Okay, and both of them, of course, depend upon if I stress something, it will deform. They're very strong functions of temperature. And when it comes to dislocation creep, because how dislocations move and how their densities form are functions of stress, and the velocity is a function of stress, they all come together to show that the strain rate is a nonlinear function of stress. This n is typically something like 3, 3.5. When it comes to grain size or diffusion creep on the bottom, if I stress something, it deforms, but the smaller the grain size, so it goes as 1 over grain size to some power, the faster it diffuses, because there are more pathways to diffuse along with these disorganized grain boundaries. So grain size plays a very important role in determining whether or not something can soften, okay? Especially if the grains become very small, it becomes very convenient to deform that way. Okay, without belaboring that. But what's important about that last diagram, this last slide, is that these are very temperature dependent. Of course, we know that rock gets cold, it's very, very stiff. If it's hotter, it becomes less stiff. And if we plot the relative stiffness, on the left, you'll see the ratio of viscosity, of the maximum viscosity, like the coldest viscosity, to the warmest viscosity, versus the convective vigor on the bottom axis. That's the Rayleigh number. You'll find that, of course, if there's very little contrast between the hottest and the coldest viscosities, it's called nearly isoviscous, which is down here. If there's a huge contrast where the cold material is very stiff because of viscosity, then the lid, the whole top lid, becomes locked up and doesn't want to move at all. Well, strictly speaking, if we look at the empirical laws, or the laws for how olivine, or basically mantle minerals, which is a lot of it is made out of olivine, how it deforms, the Earth should just be in the stagnant lid regime. It should not have plate tectonics, okay? Because the cold rock should just be too stiff to move, even if it's cold and heavy, even if it's had a long time to cool off and it wants to get heavy enough to subduct, it should be so strong that it should not subduct, okay? And this is the quandary and sort of the mystery of why we have plate tectonics. So there are plate generation mechanisms, obviously, in play on our planet. And they should be, in theory, they could be at play on any planet. So it's a question of why do they occur on Earth, or are they triggered on Earth, but not necessarily on other planets? So most terrestrial planets, as far as we know, okay, Mars, Venus, Mercury, the moon is sort of an anomaly. Okay, we don't have a lot of data points in our solar system. They undergo stagnant lid convection, which is basically what you expect them to do. The Earth is different. The Earth is weird. Okay, the Earth has these. The convection winds up leading to broad, strong plate interiors and weak localized plate boundaries, which is, of course, much of what this seminar is about, is why we have plate boundaries. But it's a unique form of convection that you have this very localized, very focused form of deformation where all the action occurs at plate boundaries. And we would like to know how convection looks like that. So it seems like the Earth has these self-softening feedback mechanisms, which means that if I deform something, it gets weaker, but where it gets weaker, the deformation will focus on that. We'll make it deform faster, which will make it weaken even faster yet, which will cause the deformation to focus on those weak zones. And you wind up getting the weak zones to sort of zoom in or kind of focus in on these narrow bands where all the deformation tends to be isolated. Okay, and that's in the essence of what's called shear localization. Okay. But also, you can get mechanisms for shear localization, but also we see on Earth that these weak zones will persist. If you develop a plate boundary, it does not go away for a very long time. And it's known that a lot of times plate boundaries become inherited or re-inherited, reused. So for example, a transform fault can develop and not go away, and then suddenly is picked up 100 million years later and used to nucleate a new subduction zone. So the inheritance of weak zones is an important feature of getting these self-weakening mechanisms to work. So in other words, what you want is something that causes weakening, and once you cause a weakening, you don't want it to go away, okay? Now, there are lots of models. People, I'm hardly the only one who's been looking at the problem of why we have plate tectonics. We often refer to this as one of the holy grails of mantle convection. It's trying to understand why we have plate tectonics. And there are models, okay, that look at put on sort of exotic rheologies like plasticity, and you put it on top of a convecting mantle, and you get something that looks like weak zones that form. So for example, where the stress exceeds the strength of the plastic strength of the lithosphere, it will deform. And if it's less than the strength, it won't deform, it'll stay looking like a strong plate. And these wind up giving you some very compelling, very interesting looking models that look a lot like these, look like plate boundaries. But the one problem is that they do not have inheritance. They don't, these weak zones don't persist, because as soon as you stop deforming them and you go below the plastic yield stress, then the plate boundaries just vanish. Okay, they only exist as long as you've exceeded the yield stress. But once you're below the yield stress, they don't exist anymore. So they're temporary. And this is a problem, not that I pointed out, Mike Gurnis pointed this out with a lot of these models probably 30 years ago or so. So how do we try to attack this problem? And this is where I get to now, is I think we're motivated to try to understand the physics of what happens at plate boundaries at this grade scale. So I make this very cheesy looking movie, okay, which I always spent way too much time making many years ago, but here it is. We zoom into a plate boundary and we zoom in on this thing called a myelinite. There's a very nice picture of a myelinite from Lars Hansen. And a myelinite, which I'll talk about at great length in a minute, is a rock. It's a metamorphic rock in which they're known for having undergone extreme deformation. And that deformation is always associated, goes along with reduction in grain size. So where there is a lot of deformation, these are prevalent at plate boundaries, where there's very extreme deformation, there's often grain size reduction, which we think is sort of one of the smoking guns, one of the clues to what is going on at plate boundaries. So understanding the physics of why grains get smaller is important. So what happens at the grain scale? If I do nothing to a rock or to a mineral that has a bunch of different grains in it, the grains will just simply grow, okay? Now, this is a movie, not actually of a real rock. This is a thing called octachloropropene. These are some really lovely movies made by Park et al. And there's actually a website I provide here at the bottom where you can go to these movies. This is actually octachloropropene, which is mothballs. I mean, I don't know if anybody remembers mothballs, but you use these to keep the moths off your clothes. And if you melt them and then you basically let it sit there, the grains in the octachloropropene will grow. Okay, see if I can play this movie a little bit more. One of the things you'll notice in this, if I do nothing to this, it's just static, the big grains will eat the small grains. So you see in my arrow, you see a little small grain, you see big grains, and the big grains eat the small grains because surface tension that is wrapped around any of these grains always squeezes the grain. but the surface tension depends upon the radius of curvature of the grain, and a small grain has a very high radius, has a very high curvature, very small radius of curvature. The curvature itself is 1 over that radius. So the smaller it is, the tighter the surface curvature is, and it squeezes the grain more, meaning that it has high pressure, and it basically pushes its mass because of the high pressure into the bigger grains that have lower pressure. So let's try to play this again. And you can see the little grains are vanishing and the big grains are gobbling them up. Okay, and that's grain growth. That's called normal coarsening or normal grain growth, which would happen if you just let the rock sit there. And this is known to happen. One of the reasons that when you look at plutonic rocks, that they tend to be small grain on the surface where they freeze quickly, but large grain underground. Okay. Now, if they put them under deformation, something else happens. The grains stop decreasing in size. And in fact, you start to see these halos around the grain boundaries that are dislocation clouds, and they start to accumulate and gather up and start making small subgrains. Okay. And these subgrains sometimes will peel off, okay, to make new grains. And in effect, the grain size doesn't look exactly like you're running the movie on the left backwards, but the grain size is actually can stall. They've stopped shrinking in size, or they can even decrease in size. Okay. And that's largely because you're causing dislocations to move around to accommodate deformation. And those dislocations will gather up near the grain boundaries. They'll connect with each other and form subgrains. And when those subgrains rotate, they make a new grain. Okay. Without going into all the details of that. But it's also noticed that grain size reduction, especially in myelinites, when you look at a myelinite, where the grains are very reduced under deformation, especially in mantle myelinites and peridotite myelinites, things that we see most relevant to plate boundaries, sort of in the upper mantle and the lithosphere, they almost always are associated with at least 2 minerals. I mean, in the upper mantle, it's mostly olivine and pyroxene, either orthopyroxene or clinopyroxene, and a smattering of other minerals like garnet and whatnot. But it's mostly 60% olivine and a little less than 40% orthopyroxene or pyroxene. And so where the minerals mix with each other, okay, where they're interspersed with each other, is where you tend to get most of the extreme grain size reduction. So for example, if you can see my arrow where it says polymineralic, that means things are very well mixed. You see these bands of very fine grains, and where it's monomineralic, you see very little grain size reduction, weakening. You see these big, strong, what's called tectonites that are just basically rotating around inside this deforming rock. So where mixing doesn't occur, okay, there doesn't seem to be much grain size reduction. Where mixing does occur, there seems to be a lot. And one of the hypotheses, I'm not the one to propose this idea has been that because of mixing, Zener pinning, okay, which is a way for it, I'll get to this in a second, how Zener pinning is how different minerals block each other's grain boundary migration. When I showed you the movie of the grain growth with the mothballs, you saw the big grains eating the small grains because their grain boundaries were moving outwards and gobbling up small grains. That's grain boundary migration. But if you have another phase get in the way, then that grain boundary migration gets blocked. Okay, and I'll show you a cartoon of that in a minute. And Zener pinning is an important component of that. It's something well known in metallurgy also to try to control grain size in metals. A nice example of this is something from my colleague Jen Gerard, who basically did grain growth experiments, but they try in some of these rock deformation experiments to keep the grain size from growing, and they dope things like MgO, which is a ferropericlase, with the zirconium oxide, the white minerals, and when you anneal it, okay, these little white blobs keep the grains from growing, and you can see when you zoom in on them that these grains, that the big grains, these gray things are the MgO, they're trying to grow, but they wind up wrapping around the small little white zirconium oxide. And actually what Jen did in doing this, instead of cutting the rock, she just tore it in half. So you could still see the 3-dimensional structure, and you can still see these divots, little pits, where the zirconium oxide stopped the grain growth because those bigger gray grains are trying to grow around them. So what happens in grain growth? Okay, here's my silly cartoon where I just, of course, treat grains like spheres. That if I have oops, I can find my cursor. There it is. If I have a big grain surrounded by small grains, the small grains have a high surface tension to them because of their large curvature, and they wind up squeezing their mass into the bigger grain. So the big grain eats the small grains. But when we have these impurities, okay, when we have a second phase sitting around, if the small grains are trying to shoot their mass or inject their mass into the big grain, that big grain has to go around the impurities because it can't eat them. Okay, so it has to grow around them, and that winds up becoming energetically unfavorable. In other words, it creates more surface energy to create these lobes and these protrusions that as it's basically trying to squeeze its way through these other little gray grains, okay, these little inclusions. Okay, so it winds up generating a higher surface energy, which is not energetically favorable. So you're not getting anything out of it. And so therefore, the grain growth stops. Okay, and that's a well-known process of Zener pinning. But it's also predicted, there's a theory that I worked on for several years that, it comes out of sort of the natural, called non-equilibrium thermodynamics. I'll show you equations quickly on this, very quickly, that how it affects damage. And when I say the word damage, what I really mean is just it's an energy exchange, okay? So just, it's not trying to be fancy. It's basically saying that if I start with a low surface energy on this big grain and I want to break it up into these 6 smaller grains, okay, then it takes energy because I have to have created some new surface energy. And this isn't all that different than, it's called like Griffith's crack theory, which basically says the energy to create a new crack is a surface energy on the new crack surface. So it's very similar to that. And in any of these models or theories of trying to reduce grain size, the one thing you have to do is you have to have an energy source to go from this low surface energy to high surface energy. And that energy comes from the deformational work that you put into it, okay? This is similar to like fault gouge is also generated, but different, okay? This is all in a ductile regime. So work provides the energy to break this grain up. But if I have these intrusions already, if the mixture has already occurred, in other words, these phases are mixed, and the big grains have to sort of squeeze them away or have to fit around the small gray grains, they already have a high surface energy. It's a higher surface energy than that circle or that sphere, and so it has a head start. And so if I want to apply deformational work to it, it's already on its way to being damaged because it's already has to have been squeezed around these small gray grains, and so the damage is easier. So Zener pinning not only slows down grain growth, but it also facilitates, it also helps you damage and break grains down, okay? And this is expressed in these equations that just a few of them, but it took a few years to derive, okay? And what you're looking at here is these are, the second set of equations are basically equations describing how the grain size grows. The top equation is expressing how the radius of curvature of the interface between the two phases, okay? So you always have an interface between, my light gray and dark gray, or between olivine and pyroxene. And that is sometimes referred to as a phase mixing area density. It all winds up looking like the same thing. You could also refer to it as the radius of curvature of that interface between the two phases. And they would naturally just coarsen. They would naturally just undergo grain growth if I did nothing to them. And that's what those first two terms mean. This Z here is a Zener pinning factor, and it just says it will slow it down. Okay, if I try to slow down grain growth, depending upon what the radius of curvature is of the interface between them that's blocking grain growth. But in the same sense, damage occurs, which is deformational work, goes into stirring up the interface, but it also goes into breaking down the grains, and that is facilitated by this 1/Z in the Zener pinning. As much equations as I really want to show you, okay? And then there's a combination of dislocation and diffusion creep here at the bottom. Okay, anyway, let's move on. So you can take some of the basic ideas of grain damage and ask the question, if I apply this to a convecting mantle, this is something done by my grad student from years ago, Billy Landit, asking if I have a lithosphere on top of a convecting mantle that has this grain damage physics to it, and I have the mantle pushing it around, what determines whether plate tectonic type behavior happens or not? And it turns out he mapped out very nicely with a lot of different numerical models that what determines this is your ratio of damage. It's kind of like how well you damage something to how quickly does it heal. It's kind of intuitive that if the damage to healing ratio is small, okay, you will basically heal away all the weak zones and you will not generate them very easily. And so the lithosphere will remain strong, and the velocity at the top will basically be zero. But if the damage to healing ratio is high, then you can wind up getting narrow bands of deformation. So these are these steep gradients between velocity. So this is the surface velocity. It's moving to the right here, to the left here, and right here would be a subduction zone. Okay, it's right over a downwelling. And you see it's very narrow, and that's basically the surface velocity is allowed to move around because the damage to healing number is very high. And so you can have a weak zone develop, okay? And so this was sort of proposed to say why you might have the difference between Earth and Venus is that Earth has a high damage to healing number because its surface temperature is cold, sort of emphasized or sort of supported by the climate, the carbon cycle that keeps the surface temperature cool. And so if it's cool, damage actually is more efficient and healing is less efficient. Okay, so healing is slow if things are cold. Turns out the damage, the way in which you can damage a rock actually becomes more efficient the cooler it is. And likewise, if it's too hot, then healing is fast and damage is low, which is maybe something like Venus. And then my other grad student, Brad Foley, who's now at Penn State, uses to map this out even further to try to understand what we might predict with or with planets and other solar systems. And really trying to map it in terms of what an astronomer would see with regard to the size of a super Earth relative to its distance to the sun. In other words, what would be its surface temperature versus the planet radius? And we were able to come up with a predictive model or a theory to say, you know, why we have plate tectonics in our solar system and whether or not we expect it to happen in other solar systems. So, for example, a super Earth, if it may be very high radius, if it's cool enough, it could be in the plate tectonic regime. But if that same super Earth was made very, very hot, it could wind up being a super Venus. Okay, let's keep going. We could also use this to address the idea of when did plate tectonics start? And I show this diagram from my colleague, Jun Karnaga, who wrote this very nice review paper. And this diagram is not really supposed to represent so much of a timeline of when plate tectonics started, more of documenting how little we know, okay, how much disagreement there is in the literature. And you'll see that the number goes everywhere from plate tectonics starting from Mark Harrison's group more than 4 billion years ago to work done by Bob Stern that says it started 1 billion years ago or even less. Okay, so we have about a 3 billion year error bar in when we think plate tectonics started. A lot of the numbers tend to sort of group around two numbers. And this is something that was pointed out by Kent Condy. Okay, one is that you have sort of a grouping of numbers that look to me like the onset of subduction, about more than 3 billion years ago, close to 4 billion years ago, sort of the onset of subduction, the formation of continental crust. Then later, it seems about 2.7, about 3 billion years ago or so, you start to see what looks like the occurrence of more plate boundaries. In other words, the development of like oceanic basalt from mid-ocean ridges, something like Steve Shirey saw sort of this evidence that there was the formation of basalt, which looks like eclogite coming out of the mantle, occurring about 3 billion years ago or so. So 2.7, 2.8 seems to be a number where it looks like you start to get a network of plate tectonics, but maybe 4 billion years is when subduction starts to kick in. So we followed that idea to say, well, how could you make that happen? How could you get subduction to occur, but then take 1 billion years until plate boundaries accumulate so that you have a full network of plate boundaries with transform faults and mid-ocean ridges? And so we applied this idea of damage and that grain damage could be long lasting. Once you cause grain damage, once you bring the grain sizes down so that the plate boundaries are weak, the Zener pinning, okay, the fact that it's a two-phase mixture, the Zener pinning stops them from healing. So not only does it make it easier to damage, but it also stops them from healing so the weak zones can persist for a long time. So we tried this out with a very simple model where we said, we will take a subduction zone that we just impose, okay, and we'll plop it right here in the model, and we'll let it go for a while to develop a convergence zone like this blue thing here, and then we'll just move it around, okay? Every few million years, we'll move it around. And what happens is that every time we move it around, it leaves behind a weak zone or a scar. Okay, and this subduction zone is more like a drip. Okay, it's sort of a ephemeral or sort of temporary subduction zone, but we're just making it up. Okay, so we just oppose a subduction zone and we move it around, and it winds up leaving behind scars that wind up being inherited, so that at the time you come around full circle, you have a subduction zone driven here, but you wind up having a passive ridge. Okay, this is a mid-ocean ridge that's spreading. You have passive transform faults that are all continue to last, to continue to localize, and a contiguous weak zone. I have these movies I made out of the same thing that give the same idea. Okay, that if I start off and I move these subduction zones around, let's see how well this plays. Oh, well, let's see. I shouldn't have done it that way. I should do it this way. Yep. Well, these movies are not going to play so well. Oh, it's going to hopefully not lock up the whole talk. Here we go. Okay, let's just, so there you see the subduction zones are moved around in the upper left divergence field. Give it one more spin. And in the end, what you see is that these weak zones are inherited so that you wind up with a contiguous plate boundary. The viscosity is weak. Where it's red, it's weak. Vorticity is strike slip shear. So you see two big bands of strike slip shear. The divergence is where it's blue is converging, which is a subduction zone. Where it's red is diverging, is a mid-ocean ridge. Okay, we did the same thing with Venus, but let's skip that. Okay, basically said it doesn't work, doesn't happen on Venus, but that's a parameter choice. Recent paper by Tarascaria looked at including some of this grain damage theory in one of his models, arguing that if you had brittle behavior in the upper part of the lithosphere and crust, and this ductile grain damage in the lower lithosphere, they would interact with each other to help with keeping subduction going. But what was also interesting about it, it wound up creating this segmentation in the slabs, almost like an oscillation in the weak zone, that is perhaps explains the occurrence of large offset normal faults in the outer rise of subduction zones. And it's a very nice little paper that Taras wrote just a couple of years ago. Okay, but now what I want to get into is some of the more recent, I just had to close off with some of the more recent work, is trying to understand how these different mineral phases at the grain scale mix with each other. As I've said before, myelinites occur where the grains, or the phases, the mineral phases, the olivine and the pyroxene, where they mix with each other. Where they don't mix, where they're still one mineral, and they don't mix, they don't seem to become myelinites. So why does that happen? How do they mix? And this is something that's a very difficult problem. We don't have an answer for it yet, but there have been several groups, looking at this. And what's nice is that we've, one of the groups looking at is David Kolstedt's group at the University of Minnesota has done work on this for years. And so it's been very nice sort of collaborating and comparing experiments with them on this. So one of the questions is, how do you get these phases to mix? Okay, it's not like oil and water. They're solid phases. Okay, so for example, if you look at a peridotite that's under shear, okay, this is work I've also been doing with Phil Skemmer, who's at Washington University, St. Louis. If you look at the deformation of a peridotite with olivine and pyroxene in it, and you kind of blow it up on where, see these small grains are where the myelinites occur, and you see the grains are mixing with each other. And how they mix with each other, how they propagate through grain boundaries is still something of a mystery. Phil and I proposed that they basically squeeze through each other along each other's grain boundaries mechanically, like toothpaste being squeezed through the grain boundaries viscously. David Kolstedt's group, sort of through a series of nice papers by Miki Tasaka, had proposed a different mechanism that says that you're not squeezing olivine through pyroxene or vice versa. What you're actually doing is you're taking an MGO unit, okay, a magnesium oxide unit off of an olivine, and then moving it on this red arrow into the middle of a pyroxene. Oops, sorry, and then that winds up creating a new olivine. Okay. So you wind up creating these new olivines, not because you're actually moving the whole olivine, you're just moving the most mobile unit, which is the magnesium oxide, chemically. So it basically dissolves on the grain boundary and reprecipitates. Both of these mechanisms are driven by deformation. This mixing does not occur on its own. When you're squeezing it, it deforms, and you always find that the phases will move from compression to tension, or basically in the direction of the compressive stresses. So we proposed, Elvira Molikova and I, was my research scientist postdoc for many years. She's now a faculty member at Northwestern University, proposed a diffusive mixing model where diffusion is driven by the compressive stresses acting on the interface between the olivine and the pyroxene. So just by a simple example, if it's just purely what's called isotropic diffusion, so I have a drop of something, like say it's an orthopyroxene, if it was just diffusing on its own, okay, in other words, if it was like temperature, it would diffuse like a circle, okay? If I applied a normal stress to the side, then it wants to diffuse in the direction of normal stress, okay? So you always wind up wanting things to go from compression to tension, but that winds up looking the way a dike actually opens up, okay? You wind up propagating along the direction of compressive stresses, okay? And if it's under pure shear, okay, it will move in the direction of the compressive stresses, which is at 45 degrees in pure shear, okay? So this is a diffusive theory for how grains wind up migrating through each other. And we can try to compare the combined diffusion theory with grain damage theory to some very nice experiments that Dave Kolstedt's student, Harrison Weisman, has run. First paper, 2018. He had a couple of very nice papers just come out this last year, continuing these experiments of taking a sample of a two-phase sample and letting it undergo shear. And this is sort of a nice summary diagram that shows in the deformation zone, you see very small grains, okay, where things tend to be very well mixed, okay? And we want to model that, or we model this experiment using our combined diffusion law with grain damage equations, which I showed you before, and in a two-dimensional model. And although it's very simple looking, it turns out to be, very computationally expensive. And I'm not that good a computer modeler anyway, but it was fun writing the code. Okay. So in the lab experiments, you can see that as you go to higher and higher strain, you start with large grains, and as they get smaller and smaller, they become more and more and more well mixed. Okay. And we could do the same thing in our model. This top thing here is basically what the blue and green is sort of what you're looking at with the experiments. It's the mixture of the two phases. You could say blue is pyroxene, or the one phase, and green is the other phase. And let's see if this will play. And when you shear it, nothing surprising happens. You shear it, and then things become very well mixed. Okay, they become well mixed because of this diffusion theory, but at the same time, you also wind up getting a high localization of shear. Okay, and you get a lot of deformation occurring. And it's hard to see from these movies, but I'll show you something sort of more quantitative as we go on. Okay, this is an experiment we're trying to work with Dave Kolstedt and Lars Hansen to run experiments for oscillating. Okay, and I'm hoping that they will run the experiments that goes along with an oscillating torsion, okay, which is something that we've been talking about doing for a while. Okay, one of the things, I'm not sure how much time I've got to do this. Okay, well, I can show this quickly. One of the things that you measure when you're looking at deformation in rocks and seeing how grain size evolves is the grain size distribution. So in this example, in those very same experiments by Harrison Weisman, you can look at the olivine grain size distribution. So this is just like a bell curve of the grain sizes, the number of grain, the vertical axis here is the number of grains you're counting, sort of normalized. And then this is the size of the grains in microns. And you can see as deformation happens, okay, the grains on the whole become smaller and smaller and squished to the left. And this even more pronounced with the secondary phase, which is not actually, it's actually ferropericlase that they decided to use. And the reason why is, you can ask me why, but it's not that important for this story, that the grain size is reduced. Well, we can do the same thing in our model, make the same calculation. What you'll see here is the grain size of, say, olivine on the top, the grain size of the other phase, say MGO or OPX. And this is the size of the bottom one is the size of the interface, the radius of curvature of the interface, or basically you could also call it the area density of mixing between the two phases. And what you'll see, just so I'll narrate it, you'll first see the two grains reduce quickly, okay, to what's called an initial steady state size that's just dictated by how they behave if they weren't mixed at all. And then you'll see the interface curvature become more and more refined. In other words, the radius of curvature will shrink as it becomes more damaged and mixed. And once it gets to a certain size, it starts driving mixing, and it winds up dragging the other two grains to smaller sizes. Anyway, this is, see if I can get this to play. There we go. So you first see they stop on the top, and then when the bottom one catches up, it starts dragging them in. I'll do this again, okay? So they stop for a while, and then the radius of curvature becomes smaller and smaller, and then it starts dragging the other ones after it. This is actually, I think, the oscillating experiment, which is, again, we haven't done the lab experiments to go with this, but you can see it, you know, the mixing has a big effect on how these grains wind up evolving. Okay, what's more quantitative and interesting in terms of its predictive ability, and then I want to go through this fast because I have a few results I want to show you after this, is how the stress evolves in these experiments. Okay, if you have something that's purely olivine, and these are, you know, pure olivine experiments by Lars Hansen, what you find is that the experiment starts, the stress jumps up, and then as in the single olivine, the grain sizes will sort of undergo an adjustment through dynamic recrystallization. In other words, they will become a little bit smaller. Okay, they eventually approach a steady state. They basically just have one stress drop to them. What's interesting is in the two-phase experiments, you often see, both by Harrison Weissman and Miki Tasaka, you often see a first stress drop. Okay, here, the experiment starts, the stress drops, like in the pure olivine experiment, and I'm showing you the punchline ahead of time. And then later on, at a high strain of like 10, there's suddenly a second stress drop. That in the experiments, when you look at the micrographs of the phases, this second stress drop occurs where the grains start to mix with each other, okay? Right, so this, right up into this point, the grains aren't so well mixed, but then at high strains, the grains start mixing. When they start mixing, then you see a second stress drop, you see another weakening effect. And we could predict this in the theoretical or in the numerical experiment, okay, in which we have a first stress drop, and then we could get a second stress drop. The first stress drop is due to damage that just occurs on the grain boundaries, because I'm basically taking deformational work and I'm pumping energy into grain boundaries, which would occur even if it was just pure olivine. Okay, this happens no matter what. So even you see it says monophase or any other one, that's the same stress drop. The second stress drop is due to the interface damage. In other words, how much am I mangling and stirring up the interface between the two phases, the olivine and the pyroxene or whatever, okay, until they wind up becoming so well mixed that you wind up having the Zener pinning winds up emphasizing the small grain sizes or holding the grain sizes to smaller sizes, which makes it weaker, and you wind up getting a second stress drop. So we could predict the second stress drop from the theory, which was very nice, but we're going to continue to do work on that. Okay, the last thing I'm going to show you in what I've got left is applying this grain mixing and damage idea to try to say something about why we have subduction zones, okay? And it's sometimes referred to as the collapse of a passive margin. A passive margin is where an ocean basin is spreading, like the Atlantic. The Atlantic doesn't have any subduction zones in it now. It's basically being pulled apart, and it's passive because it's being pulled apart from somewhere else, okay, by the subduction and the motion of plates somewhere on the other side of other continents. So something is pulling the plates apart, and the main force that exists in the lithosphere or in the thickening oceanic plate is ridge push, okay? And so that's one of the primary forces. It's not a very strong force. Probably what's still pulling it apart is subduction somewhere else. So it's passive, okay? And the question is often, why is it, you know, could we wind up getting subduction occurring at the passive margin? In other words, the margin between the oceanic lithosphere and the continental lithosphere, okay? So this would be the margin here. Sometimes it's inferred that subduction seems to occur right at this margin between ocean and continent, because where the passive margin is where it gets heavy and cold and wants to sink. So right here where the lithosphere is thick and wants to sink. But if you just applied simple rheology, simple olivine rheology, it should be too cold to sink. So this gets us to the question of what can we do to undo the cold stiffening? And that's where this grain damage comes in, okay? And so we've done other work on this to say how grain damage could soften up the lithosphere even as it's getting colder, okay? Well, we can also apply the idea of mixing to the same problem. So if I look at this lithosphere, it's under ridge push, okay? So it's just basically being squeezed in the direction of those gray arrows. And I zoom in and look at a little tiny sample of a mixture of olivine and pyroxene. and ask, how do those two grains, those two phases, mix with each other when they're being squeezed on the sides like that? Okay, can we blow this up? Let's say if I looked at this, magnified, the squeezing of this will cause the grain boundaries, especially to mix at the boundaries between the olivine peroxene that are perpendicular to the ridge push, okay? Because that's where all the mixing is occurring. So the mixing is occurring. If I blow up again on the grain boundary between these, sort of in a cartoon version of this grain boundary being squeezed, okay? The gray material, the gray arrows are showing you the direction that material is being squeezed into the other grain boundaries, or it could be chemically moving along according to the Tasaka model, okay? And the red arrows are showing you the direction of stresses, okay? So where it's under normal stress, you're squeezing the grain boundaries, but under tensile stress, which is perpendicular to ridge push, you're opening up the grain boundaries and allowing the material to flow through them. So a lot like how a dike winds up forming. Okay, so what does that say? Well, this is another blow up of the same thing so you could see it more clearly. Again, green is the direction that the grains are mixing, and the red arrows are the direction of the stress. Again, if it's under tension perpendicular to ridge push, then it's opening up the grain boundaries and it's squeezing them if it's the other way. Okay, so what does this predict? Well, it winds up saying that I look at this mineral volume fraction and I'm allowing mixing. The mixing is always going to wind up occurring in the direction of ridge push. And where it's mixing is where things mix is where you get the best damage and the worst healing. Because if the two grains are mixed with each other, you have a lot of Zener pinning. The Zener pinning stops grain growth and it enhances damage. And you wind up focusing the grain size reduction right in the mix zones, right between the blue and the green blobs, which is why you see these bands of grain size. The blue bands are small grains here in the, if I can get my arrow to cooperate, okay. In the region, in the yellow bands are just high grain size, and the blue is small grain size, and where the grain size is small is where viscosity is low. Okay, and so you're seeing where the copper colored bands are on the far right. Okay, these are weak zones, but they're weak and oriented in the vertical direction because mixing is in the horizontal direction on boundaries between the olivine and peroxene that are vertical. Okay, so you wind up getting a strong vertical banding or vertical vertical bands that are weak. Okay, they're not like perfect bands, but they wind up only organizing themselves according to what your original sort of petrology looked like. Okay, and so to sort of summarize this, if it's very, very cold in the upper lithosphere, you'll get very little mixing. But there's a very large band that can get to almost like 60 kilometers thick, where you get a lot of this vertical banding or vertical weak bands that occur. And then below that, it is warm enough that the mixing is pervasive and you wind up getting a lot of very easy damage. And this is something that we worked on in a paper that Elvira Molyukova worked on in a paper from like 2018. Okay, so what is this? Also shows that in the bands, the viscosity contrast, in other words, how weak are the bands, are very weak. They're 10,000 times weaker than the material outside of it. So this could imply that the vertical banding would allow shearing and subduction. In other words, if the plate is heavy, that vertical weak banding would make it easier for it to basically slough and bend and sink. Okay. And it basically winds up causing a vertical anisotropy. And this is something, do we see it? Do we actually see something like this in the oceans? And this will be basically the end. Okay. Maybe, I mean, this is a bit speculative, but if we look at the difference in fabric and basically anisotropy, and this is in P-wave anisotropy that's observed in the Pacific versus the Atlantic, okay? Anisotropy is usually associated with, if you have something under deformation, you'll have lattice preferred orientation. The olivines will, the lattice will orient themselves in the direction of plate motion effectively. And in the Pacific, you see a very large lattice preferred orientation. And in the Atlantic, you see about half of that. And so the Atlantic, the Pacific is an active plate. It has subduction zones all around it. And the Atlantic is a passive plate. It has no subduction zones and it has much less of this parallel or sort of spreading parallel fabric. In other words, a fabric that's in the direction of this. So this paper by Jim Garrity and others that sort of observed that the Atlantic has much less P wave anisotropy, proposed that, for example, in the Pacific, you get a lot of the shearing of motion. These are sort of these strain ellipses. Okay, these are showing you the direction of deformation in a shearing plate that give you that anisotropy. And they propose that in the Atlantic, because it's colder, that you might wind up accommodating deformation by more faulting and less by this shearing motion, and therefore you would get much less anisotropy. But we've also could propose the opposite, which is that we wind up having an overprint of vertical anisotropy, but also severe weakening. And a lot of the deformation occurs in diffusion creep, especially where these are sort of copper-colored little bands are, where you will get very little lattice-preferred orientation. LPO, lattice-preferred orientation, occurs where there is dislocation creep. But if we've suppressed this dislocation creep and diffusion creep is dominant, then you will get much LPO. So this is our alternative explanation as to why the Atlantic has less anisotropy. Okay, and at that point, I'll just stop. I think I'm kind of on time to say, I've been trying to give you my picture of why we have plate boundaries forming on Earth by looking at the grain scale physics, and then try to understand how we can apply it at tectonic scales. And perhaps this helps us explain things, why we have plates on our planet, but not others so far that we know of, how plates emerged. Maybe it started as subduction zones that then accumulated into weak plate boundaries that then connected into a network of full plate boundaries by 3 billion years. And then we dove into looking at some of the physics of grain mixing and what it might be able to tell us, both within the laboratory scale and allow us to do better comparison with experiments, and also say something about how subduction zone might have initiated in a passive margin. And at that, I will stop. Thank you very much for your patience.
Well, thank you very, very much, David. It was a brilliant talk. So we'll open the floor for any question. You can put that on the chat, raise your hand, or unmute yourself and ask a question. Anyone?
You believe everything I said? No.
Yeah.
I sure hope not.
Okay, you describe us a weird hearse. So, Joao.
Oh, okay.
Yeah.
Well, I expect a question from him. Okay.
Hi, I'm sorry. I was trying to find how to actually raise the hand, and now I'm trying to put my to screens. Thank you, David. It's brilliant to see you explaining this. I've read your chapter a few times, and you always. But one question, when you were showing the equations that you said it took a few years to come up with these equations. So my question is, how do you get these equations? Are they empirical, or they have some or a mixture of theory and empirical? How you do it? I'm very curious.
Would it be useful to go back to the equations, or probably not? Well, okay. I mean, why not? Let's see if I can find my. Let's see if I can. Here we go. Okay, I'm not sure how useful it is to actually see the equation. Okay, so no, they're not empirical. So, for example, if you I just look at grain size alone, okay, there are some standards like coarsening theories, like Lifshitz-Slizoff theory, for understanding how things coarsen, both like a nucleation of melt. So if you have a melt freezing, it always finds there's a nucleation barrier. You get like a small grain grow, or a small solid will start growing after it overcomes a nucleation barrier. So there's a lot of stuff in thermodynamics on grain growth and coarsening theory. And sometimes I think like Hillert sort of had a very nice sort of translation in sort of petrology from Lifshitz-Slizoff. So this actually comes out of thermodynamics, okay? And then doing the damage part of it is sort of extending that, which is sort of marginally equilibrium thermodynamics of nucleation and how things coarsen, okay, to include putting work into it. Okay. And so we wind up writing down, you know, in the end, when you say, it sounds fancy when you say non-equilibrium thermodynamics, basically what you do is you basically look at all the conservation laws, you write them down. And the first thing, you know, Yannick, Ricard, and I spent years writing this down. Was called a grain ensemble, a full distribution of grains. And it took us years of arguing and false starts to finally write this paper in 2009 that looked at a full ensemble of a grain distribution. It was like a 4-dimensional problem, and we thought no one is ever going to want to use this. Okay, but what you do is you write down all the conservation laws. Eventually, you write down the law for entropy production, and you just know that you don't want to violate the second law of thermodynamics. And that's all non-equilibrium thermodynamics does: is you have one equation for entropy production, and then you can extract from it different diffusion laws to make sure that you don't ever violate the second law of thermodynamics. And there's a whole field of non-equilibrium thermodynamics. So this all comes from that. And so for example, this term here, you know, you have deformational work being divided by Zener-Pinning, that actually falls out of the non-equilibrium thermodynamics. That's not empirical, that's predicted. And it's still something that we would like to test better with some other models. You know, can't test our model with our own model, but we can test it with experiments. This is something that seems to occur in nature and in lab experiments, but we would like to basically understand how Zener-Pinning can wind up making dynamic recrystallization easier. It's not a given, but it was predicted from the thermodynamics. So anyway, that's a long way to say that it's not just pulled out.
No, I was curious if it was like from kind of systematic approach. I would try to look at the experiment, see, and try to tune it, or if it was coming from the thermodynamics.
I mean, in the end, we wind up, you know, even after we had this ugly 4-dimensional theory, we said, let's just make it simpler and choose a grain size distribution and assume it's what's called self-similar, so that we can write something more easily. That's what these equations are that you're looking at now. And but we of course we want them to look like what an experimentalist sees. Okay, in other words, these will look like a standard grain growth law, which is fine, and it's easy to do that. But they are basically falling out of a lot of, you know, several, God knows how many equations. Okay.
and in the work with Taras Getty, so you add this in the code of Taras.
Basically, in Taras's code, it's one of these equations. Okay, in the end, you can, you know, there's a very simple form of these equations. You can assume the z always stays close to 0, and then you don't have to worry about all these equations. You can just use one, and that's what he used in his code. And it's very similar to what like Brad Foley and my students use, is a much simpler version of this. But we've been exploring, you know, the fully coupled version so that we can compare it to the polymineralic and to lab experiments. So yeah.
Okay, thank you. I don't want to have the monopoly, but it's great.
Sure.
Any other questions? You can put that in the chat or. I have a comment which says, superb lecture. Thank you, Professor Bercovici. I have a naive, if not embarrassing question. No question is ever embarrassing. No. Could the tidal force contribute to the early damage of the Earth, since the moon was much closer to the Earth and the Earth was spinning more rapidly than today?
Yes, absolutely. I mean, even now, although maybe an earthquake physicist would kill me for saying this, but even now, sometimes, you know, frequency of earthquakes, I don't think tides will affect whether or not you have a megathrust earthquake, but, you know, the triggering of earthquakes can sometimes be associated with solid body tides. So even, you know, when the moon was very close to the Earth, it's very possible that the solid body tides were enough to sort of enhance damage. You know, in other words, as you're having the solid body tide running over the surface of a crust, to keep it weak and allow it to continue to you know, develop these damage zones that either inherit it or allow the lithosphere to cooperate or sort of become incorporated in the whole convective circulation. So it's not at all a naive question. It's a very good question. So,
any other question, comment, or should we leave it there?
Well, if you have any other questions, by all means, pass them on. I'm happy to answer. So
okay. So well, once again, I would like to, with the audience, thank you very much for taking the time, David, to give us this talk. It was really a privilege. And yeah, so I thank everyone also in the audience to join us.
Okay.
I'll stop the recording there.
Okay. And thank you all for your patience as I dug deep. Okay. Thanks again.
Ciao.
Okay. Bye-bye.